Hello and welcome to the section of the MATLAB tutor. Here we're going to explore the Symbolic Math Toolbox and how it can help you if you're dealing with complex arithmetic. I think you've seen the pattern with how I'm handling this stuff. I'm teaching you the core functionality of MATLAB first, in this case with complex numbers, and then I teach you how it might apply to doing math symbolically. Usually that means keeping the answer exact. So let me give you probably the best example I can think of. Notice that when we did something like absolute value of a complex number, 3 plus 3i, all right? If you think about this in the complex plane, it's basically like this guy. We go 3 units in the real axis, 3 units up the imaginary axis. That lies at an angle of 45 degrees. So whenever we take the absolute value of this, let's actually change it. Let's find the angle. If we take the absolute value of this guy, and the angle of this guy, it should return 45 degrees. But of course, MATLAB deals in radians, so what it's going to actually give you is 0.7854 radians. That is a approximated answer. That's a decimal answer in radians. All right. Now, if you take the same thing, the same calculation, but wrap it in the symbol operator, which we've talked about extensively before, then basically it's going to redo the calculation, but it's going to try, because it's wrapped into this, it's going to try to keep the answer exact. So when we do it again, it's pi over 4. Again, the answer's in radians, because MATLAB always deals in radians, but it keeps the answer symbolic. In other words, exact. This is an exact answer, pi over 4. That's an exact answer. 0.7854 is, even though it's good enough for most uses, it's not exact. It's a numeric approximation. Pi has infinite decimal spaces. The division by 4 means you get another number with infinite decimals. So it's trying to keep it exact. And you can play around with this. Of course, if you do 1 plus 1i and wrap it in the symbol, it's again going to be pi over 4, which is 45 degrees, because the angle is the same in both of these cases. All right, now what if you put a different kind of complex number, 1 plus 2i? Well, it's going to be a different angle, obviously. Notice what MATLAB now does. It gives you a giant numerator of a fraction. This is a fraction. This is the numerator. This is the denominator of this fraction. That's a huge fraction, but again, it's trying to keep it exact. If you take this giant number and divide it by this giant number, you get the answer, which is the angle here in radians. If you want to convert this, just type double answer and it will convert this guy to a number, which is exactly what you get if you remove the symbol operator. And if you just ask MATLAB, hey, what is the angle of the complex number here, it's going to return 1.1071. So this exact answer we got here, not too terribly useful, but again, it is definitely trying to keep it exact for you. What if you did the symbolic angle, the exact answer, so to speak, of the complex number 2i? Well, this lies completely on the imaginary axis, so the angle should be 90 degrees, which is pi over 2, and so it gives you pi over 2 as an answer. Another great way you can see how to use the Symbolic Math Toolbox is when you use the absolute value or the magnitude function. We talked about this. If I type in what is the absolute value of 1 plus 2i, which is basically saying what is the magnitude of this complex number, then what it does is Pythagorean theorem, 1 squared plus 2 squared, and then you take the square root of the answer, and that's how you find the magnitude, and it gets a decimal answer. This is close enough, good enough for most uses. But if you take this guy and wrap it inside of the symbol operator, or the symbol function, I should say, it's going to do the calculation again, but attempt to keep the answer exact. In this case, it gives you an answer of 5 raised to the 1/2 power. So 5 to the 1/2 is the square root of 5, is basically what that is. What is the square root of 5? Well, you could just basically convert that to a number by wrapping it in the double function, and then you get the 2.2361. So it's kind of fun to go and play with the Symbolic Math Toolbox. I mean, you could type in, 84 for the real part, for the imaginary part, negative, 97. Okay, so that's a large, complex number. We write it in this format, and it's wrapped in the symbol operator, and it tells me that the magnitude of this guy is this giant number raised to the 1/2, which is the square root of this large number. Okay, so the Symbolic Math Toolbox lets you work with complex numbers and get things in terms of radicals like this here, or it gives us angles that are exact like pi over 4 like before. Or if it can't do that, it'll give us a giant numerator divided by a giant denominator, trying to keep the answer as exact as it can. Now let me show you one other example when you might use complex numbers in the symbolic math toolbox. What if we defined a variable, a, and set it equal to 2 minus 1/2 I? So we can do it like this, 1/2 I, 2 minus 1/2 I. So we hit enter, and MATLAB says, okay, this guy is 2 plus 0.5 I. All right, so that's what it would do if you were just typing it in normally. It's going to treat everything as a decimal. It's going to convert this fraction to a decimal, and then it would operate on everything numerically as a decimal. But now, instead of defining it like this, let's define the variable a again. Notice a is a numeric variable. Let's define it as a symbolic variable. Remember this command symbs, that takes variable a and it redefines it as a symbolic variable. Notice that it changes to a symbol here. It changed as soon as we redefined it. Now let's set a equal to the symbol 2 minus 1/2 I, like that. So what we're doing here is we're saying let's set the symbolic variable a equal to this complex number, but let's treat the complex number as an exact symbol, basically. So anything you want to be treated that way, you need to wrap it like that. Now whenever I hit enter, it doesn't respond with 2.00 plus 0.500 I. It returns with the exact value, 2 plus 1/2 I, or I over 2, because it's treating everything exact. Notice a is still defined as a symbol. That means it's going to try to do all calculations exactly. So this isn't going to make too much difference for stuff like a plus a, because you know that's easy. You add the real part, you add the imaginary part, and you get this guy right here. But what if you wanted to do something like a squared? A times a. So you would be multiplying a times a. You would be doing FOIL everywhere. You would have I over 2 multiplied by a bunch of stuff, and then you'd have to collect like terms and present the answer. So when we do it in terms of a symbol, a is now a symbol, the answer we get back is exact. We don't get a decimal here. We get 15 divided by 4, and we don't get some weird decimal here. We get an exact number 2i. So this is the real part. This is the imaginary part. What if you wanted to raise it to the third power? So a, this complex number, which again is still a symbol, here's the real part, 13 over 2. The imaginary part is basically 47 divided by 8. That's a fraction, and that's the imaginary part because it's 47 over 8i. So you could do crazy things like a to the power of 5 plus 2 times a to the third minus 10 times a squared. So this is something, and just to kind of keep it straight, I'll make it a little bit easier for you to read. So we have 2a to the third, and then we have 10a squared. This would be something that would take you a fair amount of time by hand. A to the fifth, you have to multiply it out, and then you'd have to do this, and you'd have to do this. Everywhere you get I squared, you have to treat it as -1, collect terms, deal with the fractions. MATLAB spits the answer out immediately. This is the real part, which is a negative number. This is the imaginary part. The imaginary part is 857 over 32. In fact, if we wanted to set and find out what the real part of the answer was, then it's going to give us exactly as a fraction the real part. If we wanted to know what the imaginary part was as an exact result, actually I'm going to get in trouble here because if I type in A and S, this is a good example of what to avoid. If I type in A and S now, it's going to use the last answer here. It's going to give me a guy of 0. What you really should do is set another variable B equal to what we did right here. So I can just highlight this. I can copy, Control C, paste it down here. So variable B is now equal to the answer that I want to deal with. So the real part of B is given by that. The imaginary part of B is given by 857 over 32. I can do things like take the conjugate of the answer B if I'd like, and it's going to treat it all. I noticed it put a minus there. That's the conjugate of what B was originally equal to with the plus sign there. It's going to treat it all exactly, and that's really what the symbolic math toolbox is for. Most of the time, especially if you're doing just a regular simulation or something, you don't really care about keeping these answers in perfect fractions, okay? If you're doing a calculation of an antenna pattern and trying to figure out how the antenna is going to shoot the radiation out or something, you don't really necessarily care if it's an exact fraction. But occasionally when you're doing math, you do want to keep it exact, and this is how you do it. You define your variables in terms of symbolic variables, and you do all the calculations in those terms, and the answers that you get should be in these exact fractional answers, or in terms of square roots or things like that that are considered exact. So try to reproduce what I've done here on your own. Dig out some other complex numbers, put them in there, and see how you can use the Symbolic Math Toolbox to calculate exact answers. And if you ever decide that, okay, you've had enough of looking at these fractions and you just want to look at the decimal answer because that's the one you really care about, you just pass it to the function double. That will take the symbolic answer and convert it to a decimal, which is what we have right here. I'm Jason with MathTutorDVD.com. Go play around with MATLAB. Focus your efforts on trying to understand this, because complex numbers are things you'll use constantly all throughout math and science.